So let me just check if we are now on live somewhere. Okay, check.
It's actually pretty cool. I'm here in Kiel. I can give a talk live.
Somewhere.
Now I hear echo. No, this was you, Alina.
Yes, that was me. But I think, yeah, we are now live. Okay, so let us start. Okay, so hi everyone. Welcome to the monthly seminar of the IEEE-EMBS Puebla section. This time we have a very special guest for me because he used to be and currently still is the chair of the Digital Signal and System Theory group where I did my PhD. It is my pleasure to introduce Professor Schmidt. Gerard Schmidt received the diploma in engineering degree in 1996 and then the doctor in engineering degree in 2001, both from Darmstadt University of Technology in Germany. After his PhD, he worked in the research groups of the acoustic signal processing departments at Harman, Becker Automotive Systems, and at SVOX, both in Ulm, Germany. And parallel to his time at SVOX, he was a part-time professor at Darmstadt University of Technology. Since 2010, he is a full professor at Kiel University, also there in Germany. His main research interests include adaptive methods for audio, sonar, and medical signal processing. He is now the spokesperson of the Collaborative Research Center that the talk is about. So welcome, Professor Schmidt, and thank you for being here with us in this new kind of style of giving talks. So you can now start your presentation.
Thank you very much, Alina. And well, I start. So hope you see all the slides. Let me check if I can click it further. Yeah, so I have actually three topics. The first one is just I would like to talk about this CRC. So CRC stands for Collaborative Research Center, and personally I think that this is actually a very nice thing. What this is in detail, I will tell you in a minute. And then I have a big part about research questions that are related with this CRC, and this means I would like to talk about a new type of magnetic sensor that we use for medical, or to be more precise, for biomedical applications. Well, and at the end, I will summarize, so this is a very short part, and give some advertisements. And to be honest, I think the slides are too long for 45 minutes, and I was hoping that I see your eyes, Alina, that you can tell me, like, now it's enough, but now you're gone. Anyhow, there should be, well, if you come back and tell me with some, signs that I should stop now then or soon, then I will immediately do that. So anyhow, I haven't tried it before this talk, so I'm not sure about the size. By the way, here you see a couple of people, students actually, master students, that do heart measurements in the shielded chamber. And shielded means magnetically shielded chamber in Kiel. And so they can actually do research here, and they see actually without touching the body of this guy who's lying there, they can see the heart signal, but in a magnetic fashion. So that's actually part of it. Good, so let's start with the CRC. It has certain numbers. This is not that important. But what I think is very nice is we have a system here that comes from a German research foundation, DFG, German Deutsche Forschungsgemeinschaft. So they fund projects. And actually, Alina was also part of one of these projects. And the idea is now that if you have an idea, for example, that you think that, for example, one sensor that is able to measure magnetically relevant things of a human person, of a human being, but you need a lot of people to really do this, and then the German Research Foundation gives you money for this. And that has actually happened about 5 years ago. So you get about 10 million euros. That's for us a lot. And then about 40, 50 people can work together for at most 3 times 4 years. And we are currently in the second period for 1 year. And you see here the couple of people. The young ones are PhD students. The older ones are professors or PIs, principal investigators. But what is nice is that all these people have the common goal to develop a new type of magnetic sensor And therefore, you need a lot of expertise and the willingness to cooperate with others. And it's pretty nice in our group here. So this starts usually with, let's say, physics. Some things happen at boundary effects of materials. And then usually it's good if you have good knowledge in physics to understand what's happening in detail there. Then, of course, you should use new materials that exploit these effects and maximize them. And you should understand how to create these sensors in such a way that they are in the perspective. Yeah, you have written this, Alina. Okay. So in the perspective that you can produce sensors that are as cheap as electrodes. That's the goal, actually. But these sensors should be able to measure signals that are relevant for medical people. Usually you want to have sensors to be really small, let's say 1 millimeter or 2 millimeters in size, and then you can put a lot of them, let's say, on your brain, on your chest, whatsoever, where you're interested in, maybe medical analysis, cardiologic analysis, or neurologic analysis. So they should be small. However, small means usually also that any resonance frequencies that you can exploit, mechanical resonances, that they are high in frequency. On the other hand, if you go for medical signals that you would like to measure, like the signal of a heart or the signals that are going on in the brain, then we talk about low frequencies, something like, I mean, Alina is an expert in EEG. I would say we start there at 1 hertz and we go maybe up to 20 or 40 hertz, or maybe a bit higher. I don't want to argue with that. But these are very low frequencies. And if the sensors are small, then they are whatever resonant at a megahertz or a couple of 100 kilohertz. So this means you must convert this in some way. And then engineers are actually a good idea to cooperate with. Or when you need, you have really small signals, so you must have low noise amplification and so on. And then at the very end, you would like to apply this on patients. So really in a hospital where you just check if this works or not with a couple of diseases that you have specified before, and then you need medical doctors. And the whole team actually works together. So all these medical people, they learned to use a language that also engineers, physics people, and others understand. And also the physics people and the engineers learn to do something that really has the target to help the medical people to do this. And since Alina is an expert in signal processing, then of course you need a lot of signal processing. That's the best part of this series. And here you see one of the pictures that we made before Alina was leaving Kiel. That's actually my office, so it's the same stuff as you see behind. And I was younger at this time, but well, anyhow, I really like to remember back to the times. This was actually at the time when I started here in Kiel. Alina was there. She was doing the PhD with the person that was here before me, and he's still here. So I like also this guy. And I think this was in your last days, or when we made this picture. Hope you have good memories to Kiel here.
Yes, of course. Yes, that was in my last days there. Yes, thank you.
And then Alina also finished her PhD there, and you see she has this hats on. So this was immediately after the defense of her work on EEG and so on. And you see also, I mean, maybe you know her husband, Enrique. And well, this is actually the guy what was supervising Alina, Professor Heute. And also, I hope you remember this. And we have written one paper together. I hope you remember this, on empirical mode decomposition, or it was a nice paper. And there was this conference in the northern part of Africa, in Morocco. And I was assuming, hey, you go there to Morocco, have a good time there. And then you told me that, oops, you will not go. And I said, hey, why? And I think this was the time when you didn't want to fly anymore because you were getting your first child, right?
Yes, exactly. I was pregnant there.
Yeah. So I got there, I presented for Alina, and I had a good time actually in the northern part of Africa. But also, I like really to look back at these times. So this is the CRC. I just want to say a few words about it, because at this CRC, I have some not jobs to offer, but stipends or internships to offer. If someone would like to go to Germany, you could ask Alina how it was there. If she says bad because of the food, Alina likes really meat, and we eat always vegetables over here. And the weather is not as good as in Mexico. But anyhow, maybe. So now I would like to come to the main part of the talk. I hope that's fine. By the way, if someone wants to ask a question, you can do this immediately. So or however Alina wants to do this. Bon dia is something like that. Okay, a bon dia also. Good. So the motivation is, and now I hope, I mean, I'm old, but maybe some of you still are Trekkies, so Star Trek people. And I have first a hypothesis. So I say if magnetic sensor technology would be able to replace current electrical analysis, then something could happen. So this is, first of all, you assume that you are positive in your research, or that you reach what you think that you want to reach in your research. And then you could check what will happen then, or what is the consequence. And the consequence will be then, well, some research questions that you can try to answer. For example, why should we switch from electrical sensors to magnetic sensors? What is the benefit over there? Which medical analyses are possible then, and what are better, or should you combine electric ones with magnetic ones? And what are practical applications that you can see? And also I will show you in a minute some results in a couple of minutes. And now coming back to this picture, this is the medical doctor. Do you know these series, Alina, from Starship Enterprise? People are not so Trekkies anymore, anyhow. So he has some in his one hand, he has something like a mobile phone in his hand. This is mainly a visualization of results. And in his fingers, he has some little device that he usually puts above any person that he would like to treat. He's the doctor there, and he didn't touch the person. And if you think what technology might be in these science fiction films or series, and then actually you come to the point that this is usually a magnetic sensor, because with a magnetic sensor you don't need to touch the people anymore. You can measure from a distance. It's a weak signal, of course, but it's there. But now let me motivate shortly why we should go for, let's say, for a heart analysis. So you would like to know the heartbeat of a person. That's pretty easy these days. So you have smartwatches that can do this, and a couple of devices. So there is no need for any research anymore. However, if you would like to know it in much more detail, so let's say you have a certain disease, example, Wolff-Parkinson-White syndrome. This means somewhere in your heart there's current flowing in order to make your two chambers to contract and to pump blood into your lungs. And let's say if you have there a certain side connection where current is flowing, but it should not flow. So you pump, and then the current goes back on a side chain and makes the heart excite again. So this means your heart would beat then with 250 times per minute for a couple of times. So there is this, this loop in some way. And if you would like to know where is this tissue where current is currently flowing, where it should not flow, then it's pretty hard to do this with, for example, an MRI analysis, so with magnetic resonance imaging or with a CT, because you wouldn't see it. It's the same tissue as where current is not flowing. If you would like to do this with an ECG, an electrocardiogram, so you could put a lot of electrodes on your chest, but the stuff that you have in your body, like muscles, bones, fat, air, actually, the lungs is filled with air, they all have different electric properties. So the epsilon R is pretty different. For finding the peak of the heart, that's easy. But if you would like to go back from a voltage that you have measured on the surface of the body down to the individual voxels, voxels are pixels in 3D, so the little volume elements, and you would like to know where is currently which current flowing as a spatial distribution, then it's pretty hard, because the voltage has kind of weird ways to distribute from the source, which you cannot analyze, towards the place where the sensor is. Magnetically, all the stuff that I have mentioned now, all the materials, bones, fat, air, and so on, they have the same mu r. So this is a pretty straightforward excitation. You can use Maxwell or simplified Maxwell Biot-Savart, and it's pretty easy to compute, or to go actually back from the sensor levels towards the source level, to the individual voxel of the heart. So this would be very nice if you know this, and then you don't need to go really inside the heart. That's what happened currently. So they put catheters in your heart, measure it a couple of times, and so you have some electrode somewhere in your heart. And afterwards, the treatment could be done again without any well, surgery. So they have meanwhile X-ray located knockout systems in order to do this. So if it would be possible magnetically, then you have an easier job, or at least it could help with well, or you could combine it, the magnetic ones with the electric ones, and then these inverse solutions in order to find, for example, problematic tissue somewhere is very easy. That should be one motivation. And now I should speed up, I think, a little bit in order not to go too much into detail here. Anyhow, I have a couple of examples or a motivation, because I think this still a motivation is a good idea. Alina said that I worked in the automotive environment, so I like to work in cars, to be honest. This was the one reason why I show this example. And the other one is because Alina and Mutu and myself worked on this topic, what I will use for motivation now. So assume that you would be here in Kiel. Kiel is in Germany. In Germany, we are proud of our cars. So a couple of other countries are this as well. So I guess that the whatever English people will also say that are proud of the Bentleys and whatever they have. Anyhow, over here, we like our cars, and we are allowed to drive without any limit. I mean, of course, the car has a limit, or the driver have limits, but not. There's no speed limits on a lot of our streets. Kiel is in the north of Germany, and now assume that you have rented a very nice weekend house, or a house for the weekend in Denmark. And if you would do this, then you have a nice empty street in front of you, and you go with your car to the north on an autobahn. And let's assume that in front of you is this car that you see here. I hope that you can see my mouse. Is this right? Okay. So what you would do, I mean, usually these cars, they have a limit. They are only allowed to drive 80 kilometers per hour. And usually they do maybe 90. And the typical speed of well, if you drive in Germany, is about 120, 130, I would say. And let's just say you see this, you would like to overtake. So you take the steering wheel, you go a bit to the left, you overtake, and you go back to the right. No big deal. But now what could happen is you have not seen this fast Porsche car from behind, and he or she drives with 50 kilometers per hour. That's possible. And so an accident would appear. And now, of course, these cars, they have radar and lidar systems, so they would see that there is something behind, but this little movement there is actually a problem, so it will lead to a crash. If you would know that the driver of your car, that you will do a movement soon that will lead to an accident, the car could easily predict that and avoid that you can do this movement. So it will just do a little bit of the movement, but not everything. But then you have to know what is the driver currently wanting to do. And now we talk about not when you think that you would like to overtake. We talk about the point when you tell your arms, move the steering wheel. So we talk about the motor cortex. Motor cortex is somewhere over here. So if I would move this arm, you would find it here, and vice versa. And it's close to the surface of the brain, so you can detect here that you actually go. And so we did recordings together, and I hope now you remember this again. So I weird as a first person a multi-channel EEG system. So it was more than 200 channels. A couple of them were actually electromyogram channels, and then we were driving. And by the way, this guy here is Mutu Mutoraman. He's meanwhile a professor in Mainz, famous guy. But at this time we did first recordings, so we drive around and we try to find out whether it's possible to see whether I do a right or a left movement before I actually do. And that was possible just by analyzing these parts or using these electrodes here. And then you see it about, I would say, 150, 200 milliseconds before you actually do it. That's because, well, you know, you tell your arm to do it, and then there must be some signaling into your muscles, and then the muscle must start work. And in total, it's about 150 milliseconds before you actually do. This is possible now, but I don't think that people will drive like this. So, for example, we have used baby shampoo in order to have a good connection. Baby shampoo is actually cheaper than the gel that you get from the vendors of these EEG signals. but after about half an hour, it dries out, and no one would really drive like this. It was fun for once, but not well. Now imagine that you would put electric sensors in the roof of the car or in the headrest, so somewhere at this position, for example, and then it's actually possible if the sensors would be sensitive enough in order to look in the brain. Right now, this is not possible, and also the sensors that I will present you are not yet ready for this. But I think in the future there might be some cheap sensors that can do this actually from a distance. So this means you can measure, for example, in the car, well, details about the brain. You could also think about measuring in the car, what is your heart doing? So sometimes there might be some beats that are missing, and if you detect that very early, then the treatment is much better. And now, where are places where you sit for a couple of minutes or hours where you can do analysis? It's for example, your car. You could also do this in the chair, for example, that I have here on my desk. But this is some permanent monitoring. But for that, you will not use electrodes. So you will not get rid of your clothes and so on. But all these practical things, then a magnetic sensor, if it's good enough, would be a very nice alternative. That's for the motivation. And finally, I show you this. That's actually was also what we learned at this time. I learned about brain-computer interfaces, and then we were trying this prediction of steering movements, but also I was trying to dictate with my brain. So you see here, I sit in front of a computer monitor. I point with my fingers towards one of the letters here, the B. And this is a video I started soon. So all the letters will flash in some way. And I concentrate now on the B, and I just use my hand in order to show you on which letter I concentrate. So I don't touch it. It's not a touch screen. And the rows and the columns will flicker. This is something what you will see, and you see little pictures whenever it flickers. For example, the B is actually a small Mariah Carey. I like her. And what I do, I count how often do I see Mariah Carey. Whenever I see her, you get a signal somewhere here in the center of the brain on the outside. So it's a P300 measure. And then you simply know when the different keys are flashing. And you could just check if the signal that you measure over here fits to, for example, the B, to the V, to the C, to the X, and so on. And the one that fits best, you can select, and then you are able to help people that cannot use their body, their eyes, and so on. They just focus with their brain on specific letters. And now I trained this for about 10 minutes, maybe 15, that's it. And then these brain-computer interfaces were working. So I played a video. You see this B. Now I go for C. So you see the flickering. It just takes a few seconds, and then the C is locked in, and then I use the I. BCI, brain-computer interface. So that's a nice idea. So, this works quite nice. Well, we can stop it here. I was hoping that you are somewhere in the background, Alina, but I didn't find you here. Maybe, were you part of this lecture? No, okay.
No,
anyhow,
I wasn't.
So what I wanted to show, that's a nice idea, but once again, you must put these kind of helmets, these caps on people. That works, of course, for an analysis in a hospital. But if you would like to help people with a handicap on a permanent basis, then it would be much nicer if you have just something that is somewhere on the top of your head, but not always sticked and glued to it, and you need contact and so on. It's another motivation here. Okay, and now I would like to come to the sensors. Otherwise, we sit here still tomorrow. So the solution is actually, I already said it, magnetically. And now you see me with a beard here. So a year ago or 2 years ago, I had a beard. I thought this was good looking, but then my wife told me it's not. Sorry. But you see in my hand here 3 printed circuit boards. And they contain the medical sensors, the small version of the medical sensor that I will talk about. And actually, this is not the sensor, this is a larger board. I will zoom in. But first of all, I would like to explain you how this keel idea of a cheap magnetic sensor is. And this is called a magnetoelectric sensor, a specific type of it. So the sensor principle. Usually you would like to convert a magnetic signal, a field, into a voltage. That's what at the end you will mostly have voltages. And there is, of course, a direct connection about a magnetization, and you have a polarization. A polarization is a voltage change, for example, or a voltage difference that you can measure. Unfortunately, this direct conversion from magnetic to electric is not that strong. There are a few effects, but we need really weak fields. I mean, just to give you an idea about it, this MRI that you have in a hospital, so these big analysis methods, they have, for example, 3 Tesla. Tesla is the unit of the magnetic flux. The magnetic field of the Earth is something like 10 to the power of -5 Tesla. So we talk about micro Tesla. And now if you look for the heart, then we talk about pico Tesla. Pico is 10 to the power of -12. And if you go for the brain, we talk about femto Tesla. Femto is 10 to the power of -15. And they are present in parallel. Of course, you could say, I don't want to measure beside an MRI, but you would like to measure beside the magnetic field of the Earth, of course. And also a power supply of a computer is also creating a magnetic field in the region of a few microtesla, maybe. So you have a strong field, which is fortunately in a different frequency range. So we talk either about high frequency power supplies or 50 hertz, which is still okay, or DC, so 0 hertz. And in the middle is the interesting part. So in terms of frequency, it's possible to differentiate, but it's pretty hard to make typical sensors that are currently on the market, like a squid or an optically pumped magnetometer. If you excite them, or if they see this magnetic field of the Earth, they will not work anymore. So they all need to have a shielded chamber, a magnetically shielded chamber. That's not practical. If you go for a medical analysis, they must work in a typical medical environment. And this means there's a lot of devices beside you that help you to survive. And they are all creating a small magnetic field at 50 hertz or whatsoever, but this is necessary. And so the idea, now I come back to this sensor, is actually that first of all, we have a magnetization that we convert into a strain, so a size change of a material. And then the size change is coupled mechanically towards a piezo layer. And then the piezo layer can be used to read out. And so there is some geometric shape in between. And this is something that you can exploit in order to boost the signal. So because there are resonance effects that might be used. And here you see one principle here. So you take a substrate, a cantilever, usually made out of silicon. This is, in our case, for example, here, 3 millimeter long, and height is virtually nothing. And it's clamped on the one side. So it's something like this, what you see over here. So it's clamped here on my hand, and then it could vibrate, right? So you put on top or on one side a so-called magnetostrictive layer. This means when you apply there a magnetic field like B, then this layer is actually, well, being longer in length, and so the cantilever, if this part here is enlarged, will go down. If it's the opposite, it will go up. So you make the cantilever move with a magnetic field, and then you can put a piezoelectric layer here on the other side. And if this happens, then the piezo layer will be enlarged, and this leads to a voltage, or vice versa. I have a little video that this makes it even clearer. So right now, this is just a magnetostrictive layer here, the blue one. And if you put a magnetic field, the blue arrow, then this material is actually enlarged. It's FeCoSiP. Fe stands for iron and cobalt, silicium, and bore, with different numbers of materials. If you put this now on a single-sided clamped cantilever, the cantilever will move. And now you can put either on top or on the other side a piezo layer. This is the red one, which will appear soon. And then this movement will be converted towards a voltage. And now you see here the magnetic field, and here you see the voltage, and then you have something that you can use for measuring. And now maybe I don't know, in Mexico, I guess you have a lot of pools, as we have in Germany. But I'm not sure if you have these boards where you can jump into the water. And then usually these boards, they are clamped also on one hand, and then there is something which you can move, and then you can jump. And if you adjust it such that that the resonance frequency fits to the weight of your body, then you can jump pretty high. And if not, then not. I hope you have realized this. There is not much difference in these pool cantilevers, but still, I would say maybe 30% higher jumps are possible if you adjust them. In these bars here, we have an improvement in resonance of about a factor 1000. So there's a lot of boosting, and this is something that we can exploit. Okay, now I zoom in these cantilevers. Currently, we make them mainly at the size of 1 millimeter times 3 millimeter, and the height is virtually nothing. But we have a cooperation with the Fraunhofer Institute, and they make it really small. So you see again this picture here with these 3 printed circuit boards. Then I zoom into my hand. You see again these circuit boards. And the stuff in the middle, this is actually the sensor, or a couple of sensors. And now I zoom in here. And then you see this is 1 millimeter. And these little things here, these 5 fingers, they are the sensors. So they're pretty small and pretty cheap. You could put a lot of them somewhere where you want. And they measure actually the, if you need them small. Usually this is a bit, I don't see this anymore with my eyes. I mean, I need glasses, but usually we make this a bit larger. But if we need it, we could make it really small. So first, small size is actually solved. They work in parallel to magnetic field of the Earth and other strong fields, but we have not yet reached the sensitivity, so that the noise level is still too high, but still high enough in order to come close to the stuff that we want to do. This is not the, I mean, I told you now the very simple readout scheme. I didn't tell you something about how to convert frequency. And to be honest, the talk is not long enough to go into all details here. I just would like to show you 1 or 2 possible solutions to that. One is called DeltaE. It means that you have an extra electrode on the cantilever, and you excite this cantilever with a frequency that is somewhere in a mechanical resonance of the sensor. For example, these 3 times 1 millimeter sensors, they have resonances at 7 kilohertz and at 50 kilohertz. Let's say we take the second mode, so 50 kilohertz. So you make with a voltage, you make the cantilever vibrate at this frequency in resonance. And what happens now, if there is an extra magnetic field, then the magnetic field changes the E modulus, so to say the stiffness of this cantilever. And this means if the stiffness is slightly changed, you excite not in resonance anymore if the magnetic field has changed, but slightly beside it, or if you are beside, you come in resonance. And so the kind of the resonance frequency is shifting independence of the magnetic field. And if you excite now with a constant voltage and a constant frequency, and then it will create an amplitude modulation because of this E modules change. And this means now you can do a readout at 50 kilohertz, but a very low frequency field is actually manipulating the signal. And this leads to a readout that goes down to an LOD, a limit of detection of a few tens of picotesla. So such a sensor has a range of 0 to 2 kilohertz, or not 0, but let's say 1 hertz, but up to down to really nearly DC. And then it depends on the size of this sensor up to whatever, for example, 10 kilohertz, around 50 kilohertz. So this is the excitation frequency. So your readout, or the hardware that you need for readout, must be designed to handle 50 kilohertz. Another thing is that we talk about love waves quite a lot in the CRC. And this does not mean that we love, of course, we love ourselves, the other people and ourselves as well. But love is actually the name of a guy. And this was a specific type of wave, a so-called shear wave on a guiding layer. So you produce, for example, a material like FecoZip, the same that we have on this cantilever, the magnetostrictive material. And you excite this, maybe you see it over here, with IDT electrodes. So these are finger electrodes, like this is the one electrode, and the other one is like this, but they don't touch, of course. So I don't make a short connection, and you excite this with, for example, 100 megahertz. So you create a wave. And now the wave travels like this, and it's important that this is a shear wave that goes like this on a surface. If this is the surface, then the shear wave must travel like that, and not like that. That's important, because then you have much damping. And what happens now, again, if a magnetic field is applied to this, it changes the properties of the material. And this means that the delay that you're traveling along, in such materials, you have a wave speed of about 5 kilometers per second, something like that. But this is changing actually in dependence of the magnetic field. And so you measure more or less the delay or the phase of this receiving signals. So here you excite here on this side, then you have a couple of millimeters of this material, and then you have another readout electrode in the same fashion, these IDTs on the other side. And depending on what field is there, it takes longer or shorter that the waves are traveling. And this could also be exploited. This leads to something that has actually a very wide bandwidth of readouts, so about a megahertz, way too much for direct human signals, but we still have some signals like deep brain stimulation stuff that actually go high in frequency. So it's artificial signals that are somewhere in the human body, and that can be read with such a sensor. Again, we optimize it, so maybe we reach the final goals in terms of sensitivity, that we can do something with it. Maybe not. That's open. That's research. And I skipped the third one because I think we have already now more than 30 minutes. Alina is still smiling, but well, let's short talkly about applications, and then you can tell me that I stop at some point, right? Okay, we have actually 4 the CRC. So we have cardiologic applications that we target, cell applications or biologic ones, movement analysis of Parkinson patients, for example. And in the neurology, we don't go directly for the brain. That has stopped because we are not sensitive enough. We go for deep brain stimulation. So if you have, for example, if you have Parkinson and then you get electrodes in your brain that knock out certain regions. And I have examples for all 4, but I will check from time to time your eyes. Let's start with the cell analysis first. So I talk about this part. In short, it means that you make cells eat paramagnetic particles. This means they are included in the cells. And if you excite these particles, like let's say this is a particle here, a little one, that has actually a magnetic moment. If you put an external magnetic field on it, and let's say the external magnetic field would make these particles rotate in a sine fashion, but these particles will not respond directly. So they start, and then after a while they flip, and then they wait, and when they come back, they flip again. So a sine excitation would lead more to some sort like a rectangle response of these particles. But this means now that you can excite them with, for example, 1 kilohertz, and you have now a sensor that is very sensitive at 3 kilohertz. And because of this nonlinear movement, you create with the particles that flip signals at 3 kilohertz at the odd multiples of the basic frequency. So this means you can have a sensor that is not responsive at the excitation frequency, but responsive at multitudes of the basic frequency. And this is something that you can do a readout. And then you could put a sensor over the cells or over this and estimate a lot of things. And then with the help of signal processing, you can try to invert that and estimate the density of the cells. And now if the cells are growing, and then usually you make a cut and try to find under a microscope where they are. But if you don't want to do this, if you don't want to destroy the tissue, for example, you can actually read this in a magnetical way. And there are ways to put in these particles into cells without destroying them or without modifying them a lot. So that's the basic idea. Some problems. Well, what is a good excitation field? And the cells are pretty small, but compared to a cell, we have actually large sensors. And then Alina knows this, that inverse problems are really tough, but fortunately we are tougher, or at least the people are tougher. And there are a lot of more problems. Just the first examples here, you see, the system that we use. So there is a couple of compensation coils. because you would like to get rid of the magnetic field of the Earth, and then you create with a Helmholtz pair the opposite field, and then you can knock out in a certain area here the external fields if you want. In addition to that, you can use these coils in order to excite, because you must excite the particles that they flip. And then you have here a sensor holder, and then actually in the future we will have a lot of sensors. At the moment we have just a few. So instead of measuring now in parallel, we measure with a couple of sensors at a certain position. We move them by 0.5 millimeter, we measure again, and so on. And this was now a first 2D measurement. So they had a plate, and then they put some sort of a hole in it with the, this is actually CRC in German, so Sonderforschungsbereich SFB, and then the number. And I would say that the size or the thickness of one of these numbers is about 1 millimeter. So this is filled with paramagnetic particles here. So we know the truth, right? So assume that the cells have grown in this field. Then you make a measurement, and you simply depict here the magnitude of the measurement. Of course, you can measure X, Y, and Z at different positions. So they have a couple of measurements here, and this looks like that. And then we had our first inverting software or algorithms that go from the sensor level back to the source level. And then the idea is to find something that looks like CRC or SFB 1261. Of course, it's not perfect yet, but at least there is a light at the end of the tunnel, more or less, that we can see. So maybe this S is visible. Maybe I think this looks like a P. It should be an F, but anyhow, that's the first results. And this was promising enough that we say we continue with this and now go for 3-dimensional analysis. We change the excitation field. At the moment, or before, it was a fixed field or a constant field. Now we go over to gradient field. This is actually from a condition number perspective better, but this is the next job of the next PhD person. One more application, Alina, or should I stop?
No, please go ahead.
One more, okay? Or I will ask you this
Many
again.
more, many more. Yeah, don't worry about the time. You just give your talk, and yeah.
I
Go
know
ahead.
it's 10 o'clock, and I start becoming hungry at 11. So
Don't worry.
okay. Anyhow, the basic idea of the cardiologic application is that we measure magnetically and electrically the human heart activity. And I already mentioned it. We are not going for just the pulse. That would be easy. This is possible soon, I would say. The goal here is to go really from a source level down to, from a sensor level down to a source level. If there is some current flowing in the heart where it should not flow, or vice versa, if there should current flow, but it's not doing it, then we would like to detect this. So measure the heart and then go back to all the, we call it voxels, so 3D pixels. So little volume elements, and each volume element, the size of these volume elements is typically 1 millimeter in size. And then we say, what is the current in X and Y and Z direction? And we know from MRI measurements where it should flow in a typical way for this specific heart. And then we can reconstruct where it really flows. So that's the goal. And then let's see what happens. And this is exactly the stuff that you have worked on, Alina. So the stuff Kalman-based well, but not the stuff of Andreas anymore. We go a slightly different way. It's real time now. So we have really a lot of electrodes. We have now a system with, I don't know, 144 electrodes that we can put somewhere on this area here on the backside and wherever we want to, plus a lot of magnetic sensors. And we go on one hand for our own CRC sensors, and on the other hand for optically pumped magnetometers. They are able already right now to measure the heart magnetically of a human being, but in a shielded chamber. So it would be, of course, possible to measure this stuff in a shielded chamber. Of course, we want to go for normal environment, but that's the future. And the problem here is we have two nested optimization. One is tough and the other one is even tougher. So, but let's see whether it works. As first measurements, you see here a guy, and actually we took one that does marathons at high speed in low time. So he has really a strong heart. This is the strongest heart that I have ever seen. So each beat is about 5 times stronger or larger in the peak compared to mine, but the heart doesn't beat that often of this guy anyhow. So, and we had measurements here. And we had done this with optically pumped magnetometers, but also with a new type of sensor, a converse magnetic sensor. And it's not yet good enough, to be honest. This is the sensor. It's actually a new principle. We have this cantilever inside. And now we excite it electrically, and we do a readout with this pickup coil. So we do actually a magnetic readout outside. So it's a bit inverse compared to the stuff that we usually do. But this was pretty promising, and we tried to optimize this one as well. It's just that you see it. And this is the first results that we have. So you see here a time axis that is roughly half of a second, so 450 milliseconds. You see here the amplitude in picotesla. So this is about 100 picotesla, pretty strong heart. This is the QRS complex. And then we have here a little bit of a P and a T wave. At least this one might be visible. The red curve is actually more or less the truth. That is the optically pumped magnetometer. And our ME sensor here is already averaged over 60 beats, so about 1 minute. So you need to know when the heart is actually beating. So this could be triggered electrically. And if you overlay them and average them, then at least you see the R peak. So this is not yet good enough in order to do this inverse analysis. But the idea is that we start with other sensors, for example, these OPMs that are good enough, and we develop the signal processing algorithms that as soon as the material science people and all the others improve the sensor good enough, then we can simply switch to the other type of signal or of sensor. But that's current state of the art. It's still open whether it will work or not, but that's usually when you do a risky research. Okay, I look again in your eyes, Alina. Go on. Okay.
Yes, go on. Yes, please.
Brain analysis. So the brain is even weaker compared to the heart. So we decided not to go directly for whatever the stuff that I have presented to you. That's more the future. So if possible, maybe another type of sensor technology will be able to measure in the presence of the typical fields that you face. Right now, we decided to go for deep brain stimulation, people. So we measure the magnetic field around a human head in order to see where exactly is the deep brain electrode. And we have a cooperation with one of the leading companies, Boston Scientific, that produces these electrodes. And we would like to know which tissue in the brain is excited exactly with this. So before they had a couple of ring electrodes, a couple of rings were on one electrode, and you can say excite over there or there. And so you knock out a certain part in the brain. For example, if you have Parkinson, then some parts create this tremor movements, this something like that. That's actually a network of stuff. So you more or less knock out with a signal of, let's say, 130, 140 hertz, so little peaks, current peaks or voltage peaks, you knock out a certain area. Of course, the area should be as small as possible, but cover the problematic area. But you have certain areas in the brain that are, for example, good for the speaking properties or the listening properties or whatsoever. And if you can really narrow this, then it's actually a good idea. So, and we would like to know, on the one hand, where is this electrode? What is the orientation of the electrode? Because that's not that easy. And then finally, what is the field strength if you excite in a certain way? Which area of the brain, the volume of activated tissue is the name, is knocked out, and make this as small as possible. So here you see our setup. This is actually in a shielded chamber still. This is Mevlut, he works on this, plus neurologic people. This is a so-called scanner. At the very end, we will put a hat on the person and then have a lot of sensors. But right now, we don't have that many. So there is a device that can rotate around the head and move up and down, and actually also rotate the sensor in different ways so that you can do a lot of measurements around the brain. And we have also a phantom. This means this is a setup which is filled with salty liquid, such that it has roughly the same properties as a human head. The pacemaker is usually implemented somewhere here, and then a cable goes on under your skin to the place where you enter these electrodes. And then this is hard to see, but there is the electrode that goes in. Usually you have two of them. And so this is what we would like to measure. And this is the electrode. And before they had these different rings, and then you can excite just, well, specific type of geometries. And now they have sections of rings. So instead of a full ring, you just have, you know, like something like this, 3 parts for one electrode. And then you can just check, excite with this electrode versus that electrode, or this one versus the other one. And then something like this is the volume of activated tissue that you can try to measure. Where is this? So is it sufficiently activated? And are you sure that you don't excite other relevant branches? Now, if you look for the sensors, this is actually this surface acoustic wave sensor that we have. It's actually 3 of them are connected here. So you can put a couple of them. They're pretty small also, not as small as the one from the Fraunhofer Institute. But this allows you to measure up to 1 megahertz. And now if you check what about the signals, this is actually a very short peak. So it excites with 100 hertz or 120 hertz or something like this. But it's a very short pulse, and then you wait, and then the next short pulse. And so this means you have more a rectangular like shape. And this creates here these patterns that you have, well, on 100 something hertz, and then the next multitude of it, and so on. And you see over here, this is 10 kilohertz. You have still up to 10 kilohertz signal components of these excitation. So the more you measure, the better it is. And you can average with this, because you can put the people in well, somewhere and then wait for 30 seconds and measure 30 seconds and average over 30 seconds. And this is a time domain signal that you see here. In blue is just without anything. You just see the signal. And then you can first of all put a low pass filter, a high pass filter. So you attenuate here. And also you attenuate the high frequency. So in total a band pass filter. And then you can average over the different beats. And then you see this red one here. And then it's pretty clearly visible when they have the signal. And even they have a little negative amplitude afterwards. So this is really the signal that was created by the pacemaker, but measured somewhere around the head over here. And now take these signals and the distribution over all of your brain and recover which is the volume of activated tissue. And this is so far that even this company said it's worth for us. We invest in you and we be part of this CRC in terms of a transfer project. So we try to move these results that we have towards a company that they can use the results in their products. We don't get money from them, but it's just, well, it's actually a good idea, because a university cannot build up systems that are really put inside people, but companies can do this. And this is why there is, at the very end of the CRC is always a potential transfer, and this is with one American company. And now I think I should stop, or because I have an advertisement at the end.
You can go on. There is no problem here. We eat actually at 2 o'clock, so don't worry about eating or something for us.
You are at 2 o'clock?
Yes, we eat at 2 o'clock normally, so
Oh, I don't want to talk that
so
long.
don't worry.
No problem.
No, but don't worry.
Anyhow, I'll make it really quick now. So another issue that we thought is, what about the movement of, for example, Parkinson patients? Of course, you can use a camera system in order to see what they do. For example, when a movement is changing in Parkinson patients, then the risk that they fall might be high. But therefore, you need to understand the micro movements permanently. And one way would be that you do this with a camera system, a lot of cameras, and you get little, dots somewhere on important parts of your body, and you follow these dots. That's possible. But then you need to stick cameras all over the flat or whatsoever. As soon as you go out, that's not possible. You can do this with IMUs, inertial measurement units, so acceleration and gyro sensors. That's true, that's a good idea. But they have the problem that there is an offset that you always try to find, because they measure acceleration or angular speed, but not position and not angle. So, and the idea was that we put a couple of transmitters on closes, little coils, actually something, well, maybe you see this here. So these, I don't know what the word for this is, buttons? A button, yeah, right. So instead of using buttons, we will print them with a 3D printer and put a couple of coils, well, on the inside of these buttons, and then we have little senders, little transmitters. And we can excite each of these buttons on the closes with a different signal. And these signals are orthogonal. So let's say a little bit of noise or of a chirp or whatsoever at 5 kilohertz, and the other chirp is slightly different at 6 kilohertz, or noise type of stuff. So you can do the typical access principles like time domain multiple access, or frequency domain multiple access, or code division multiple access. And so this is the one hand. On the other hand, you have sensors, and since the coil signals or the senders are orthogonal, each combination, each sensor can measure each coil individually. So you have really, if you have 10 coils, you have about 10 times 10 sensors, 10 coils, 100 different pairs that can be put somewhere on the human body. And since the sensors are really sensitive, you don't need much current for the coils. That's a nice idea. So you can use a couple of batteries and do it for a day of a measurement. So of course you must refill in the air in the evening, but since they are that sensitive, then you can do this. And the other thing is these coils can excite at very different frequencies that are not typically distorted. So if you do a movement, it's actually pretty slow. And if you use, let's say, 5 kilohertz or something like that, or 50 kilohertz, then there is no distortion. So it's a pretty nice, SNR environment in that perspective. Okay, the problems are now that you don't know where the sensors are because they are put somewhere on your closes. Of course, you know roughly it's on the left arm or right arm, but the closes is actually moving with respect to the human body. So that's not that easy. And we have pretty nice localization results, but yeah, it's not trivial. But the first attempts are also quite interesting, or quite promising, so to say, that you can really detect stuff where IMUs have problems. So like pathological movements that are interesting for us. That's the setup. That's one of the jacket. It has these bullets. So we use a video system as a reference system. But in addition to that, we have coils and stuff on it. So this is the little sensors that we use. This is actually a sensor. This is a PCB board that does all the amplification and signal enhancement and so on. And these are the coils that we use. They're actually a bit larger than my buttons here, but I would say something like 15 millimeters or so. And this is what you can measure. So we have simulated movements and then real movements. Simulated is the dotted line, and we can check for different speeds here. And the simulated ones and the really measured ones, they are already pretty close. So this project has just started, but I'm pretty confident that this is actually a nice idea. And I will show you a result of localization. This is the last part of it. This was the starting part. So, I mean, for the movement jacket, you must localize sensors. Where is the sensor with respect to a coil? And when you do conventional EEG or whatever analysis, on the one hand, you need to know what is the signal of the individual sensors, but on the other hand, also the position. If the position is unknown, then the inverse solution, going back to the current in the heart or whatever, is a problem. And then we just check, is it possible to do a localization of a sensor in parallel to measuring with the sensor? Since these sensors have a couple of resonant modes, we can say in one mode we do the localization, and in the other mode we do the measurement. And first of all, it was possible that this is possible without any disturbance of the two things, localization and measurement. And here you see a real-time system that we use for this. I mean, Alina, you also you helped a student program in it. This is still alive, and now we have a dark mode. I prefer the dark mode. Christine actually prefers the light mode, or the bright mode, sorry. And so we can actually localize a sensor somewhere in space. And I show you now a video. This is Christine. She's continuing doing that. So for this setup, this is the sensor. Christine will move the sensor somewhere. She works in project B2, so she tries to move it in the shape of B2. And we can localize the position plus the orientation. So the sensor could be like this, or like that, or like this. No, I moved my hand, but if you see it as a point, then you must know X, Y, Z, and the three angles in which the sensor can be. And we can estimate both at the same time in real time. So I try to play the video. So Christine will appear soon. At the moment, there is a trajectory depicted. So you see it has still some noise. It's not perfect. And now she will move it, and you should focus here on this. So you see that the B is actually depicted. I'd also check about the orientation. It's always like this, and the sensor also looks in this direction. It doesn't look like that. So this should be a B, and now she tries to move it 2. Yeah, and this is a single sensor. If you combine a couple of sensors and you know that they are sticked together, then it gets much better. That's the next step, and that's possible. So I'm also excited about that. Okay, now enough. Excuse me. Now the outline and an advertisement. I know that I cannot listen for more than, it's an hour now. Sorry. Okay, quick. I showed you the CRC. I like this thing that people go together for, really, from the physical part over engineering, over material science, until really using this on patients, and everyone has the big view of this. This is something that I really like. Sorry. And then I showed you here some motivation why we should go for magnetic sensors. I don't say that our sensors are the best solution. There's a couple of attempts, but at least I would like to show you what principles are used in this Kiel area. So magnetoelectric sensors, maybe they win, maybe not. Let's see. I have showed you this principles, shortly the direct readout, and maybe surface acoustic wave sensors and DeltaE ones, and then a couple of applications. And I want to close with a little bit of an advertisement. We have actually fellowships that we offer for master students. It means either you have an idea of something, or you say there's an existing idea that I would like to follow, that you could come to Kiel. If you can apply for it, you get actually, here 1,100 euros per month. So usually these things last for 6 months. Otherwise, it takes a while until you understand really the problem and learn how to use the tools and do the measurements. So I wouldn't say that 3 is actually a good idea, but usually it's 6 months. Well, and then we have a website that I can also share with Alina. I can also show it to you. And there are usually something is offered. But also, Alina, if you have a nice idea that we could try out, it should have to do something with magnetic sensors. But of course, you can combine electric and magnetic ones. So, for example, here is respiration monitoring. So the idea is put a little coil somewhere in the belt of a car and put a sensor in the seat. And since when you breathe, the belt is moving a bit like that. I mean, less than that. But you could try to estimate respiration in a car using a magnetic sensor and a coil that excites at a specific frequency that is very robust against noise. So it's a specific signal that we can try out, and others. So it's just if someone is interested, either write me an email. Here you see my email. Maybe we can put the site in the chat. And that's it now. Sorry for being long. So thank you for your attention.
Well, thank you for your very interesting talk. I actually missed some of this part somehow, but it's really, I mean, it's very nice. And I find this very interesting that you already have some biomagnetic sensors already constructed, because in my time we didn't have any. And now you have a lot of this, and you can explore and exploit many of these characteristics of this kind of sensors. So thank you for your talk. I don't know if some of the students have
There's one question which I didn't see.
questions.
Carlos was confused about how external magnetic fields are filtered. Is it possible that people can say in more detail what they want to know?
Okay, Carlos, could you please write more details about your question? I think maybe if you have some kind of filtering to filter the
Yeah,
noise.
okay. So you should know about communications. I don't know if the idea of match filtering is something. So when you look, for example, how GPS is working, a satellite is sending a signal, but you know the signal. And then you can actually put something that we call a matched filter. This means the send sequence is put in the impulse response of the filter, and the filter needs the temporarily reverted impulse response, and then you improve the SNR. It's mainly that the signal is much longer, or is quite long, and this helps to be compressed at one time point in order to get a large peak, and so you can improve SNR. And this is used for all these transmitter receiver parts. Then you, if you have whatever a certain amount of SNR and this is not sufficient because the sensor is not good enough, then make the send signal a bit longer, and then you need bandwidth of the sensor, and then you can help that. And also you can make sure that one send signal convolved with the other impulse response or pattern is actually creating no peak. Only if you have the same send signal with the corresponding impulse response. And this means that the send signals should be orthogonal. This is a mathematical property, like two sine signals are orthogonal if you have specific relation of the frequencies and the sizes and so on. But also you could create pseudo noise sequences that are orthogonal. That's actually the stuff what we use, and this is roughly the stuff what in GPS systems is also used. The satellite signals, all the satellites are orthogonal to each other, and then you can actually measure a couple of satellites and do all the stuff that you do in GPS. Hope that was your question.
Okay, let's see if Carlos writes something else, but if not, then I think that's very nice for you of you to give this answer. We have one more question from Miguel. If it is possible to sense biological forms, is it possible to sense some molecular forms as virus using this technique?
To be honest, I'm not an expert in this. So we have this cell stuff, and I guess that cells are, well, we don't go for, we go for the cell density. That's different. So I would say that this is too small. But to be honest, I would recommend to talk to Christine Seelhuber-Unkel about this.
Oh, okay.
Or maybe you could. She's really good in that. Personally, I would say it's not possible. You should go for larger structures, maybe in the future, but right now I'm not sure. But for details, then Christina might, and she's a nice person, so she usually answers questions from people, especially from Mexico. We have actually a girl from Mexico, Hancheles, or is her name. You know her?
Yes, yes.
Okay.
I think it
So
was a student from Enrique, I think.
yeah, so I mean, you can directly ask Angeles, and maybe she says the opposite what I did. I'm not sure. I'm not an expert.
Okay. Well, I actually have one question for you.
Ooh, this is the tough stuff here now. Okay.
No, it's about the ECG sensors because you told me, and now you also explained that you have a 144 ECG sensors.
Hmm.
And I think, of course, they are electric sensors, no, they are not the magnetic ones.
That
But
would
how
be
did you put all of this together in the chest? I mean, they might be very tiny, probably.
Mhm.
Or
Yeah, this is actually, we didn't try this. I mean, we have a torso, and we started to glue it somewhere, and
Mm,
after a while, it's full. So
yes.
either we take really sick people, that's the one option, and the other one is, I don't know, it was just we ordered as many as we can, as we have money, and then they
Mhm.
said, well, go for 144. This is current. I mean, right now we make sure that we can read these 144 channels in real time. So Kirat has this connection of all of them. That's
Wow.
no problem anymore. And
Uh-huh.
also processing them is not an option. But to be honest, I mean, you put them on the chest and on the backside. So since, I mean, usually people don't put electrodes, cardiologic people put electrodes somewhere on behind because the lungs is in between. But if you have a
Mhm.
really good inverting algorithm, inverse solution, then this is actually also, and the same is true for the side. And beside that, you could, practically, there's no difference between an EEG and an ECG. So it's an electrode that you glue somewhere. So we decided to have as many as we can get, and 144 was just, I don't know, maybe, I guess that I can put more electrodes on Enrique compared to you.
Yes,
But
probably.
so we look for really, you know, tall people and large people.
Yeah, okay. And about this ECG or MCG sensors. I think once I ask you if you have tried this kind of sensors in pregnant women with
Mm-mm.
twins.
You would like to differentiate the two heart. I mean, first of all, pregnant is not that easy, and then pregnant women with twins. So you would like to measure 3 hearts at the same time, right?
Exactly. Yeah.
Hmm. No, we have not done it yet. So we are happy if we could measure healthy people and people with certain diseases.
Okay.
But this means, I mean, being pregnant is not a disease. So, well, if you have a project and then we can start working on that, why not?
Mm-hmm.
The problem will be to find pregnant women. I mean, we have the ethics clearance for a couple of things, and I think we could also include this. Right now, they have specified a couple of diseases like Wolff, Parkinson, White, and others, 4 different cardiologic diseases. This is okay. We can go in the hospital and measure these people. Maybe we can do an add-on for pregnant women with a good reason for it. And if we just talk about, I mean, the sensors do nothing. They are not active. So they measure passively magnetic fields, electric fields. So this is not a big deal for an ethics bottom.
Mm-hmm.
But I think you would like to go for source separation, right?
Exactly.
Heartbeat of
Yes.
child 1, heartbeat of child 2, and until now we have just thought about pregnant women, but not pregnant women with twins or even 3 or 4 or whatsoever. No,
Yes.
you go always one step forward. No, we have not yet measured. So that's the answer.
Okay. 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 That
But
will be, I think, very interesting, no? Because
right.
there you will see if the magnetic sensors are really good enough to differentiate between one and the other ones. Well, actually,
Yeah,
there's
I mean,
also processing techniques, but
this
yeah.
this would be nice for the. We have optically pumped magnetometers. They are you can measure from a distance of 10 centimeters very nicely a heart. So it looks a bit different, the magnetic signal compared to the electric one, but the QRS complex, the P wave, the T wave, this is the same.
Mm-hmm.
But still, it looks a bit different. But it's no problem. I mean, at least in the shielded chamber, then we can really measure magnetically. So
Okay.
that would be easy. No. And
Okay.
you have now a vector field. You don't measure, these voltage differences. You
Mm-hmm.
measure really, well, X, Y, and Z components. We actually measure the heart axis. This was a PhD, not a PhD, a bachelor student's work. So
Mm-hmm.
the heart has a certain axis, differently for most of us, so slightly different. It's just important whether the heart axis is moving over months, and then it's a disease actually. But electrically, you measure it only in this area. But
Mm-hmm.
magnetically, you can measure it also in that area, so completely 3D.
Mm-hmm.
This works nice. Maybe for separation, source separation, this is also a good idea.
Mm-hmm. Okay. Yes. Well, thank you. I don't know if Enrique has some more questions.
Yeah, I wanted to comment about something. Yeah, it's a very nice talk, Gerd. And
Thank you. It's an honor.
yeah, it is very nice how the project has evolved in the time. I remember when I was working also there. I was not part of the SFP, but some of my colleagues were working there, and it was interesting that there were many different concepts being tried at that time. All the profs from material science, and some people from electronics, and the people from the medical part and the physics part and signal processing, all were coming
Yeah.
together. But they came to know each other at that time, I would say. But you were trying different things. But now you started presenting this part of the magnetostrictive and the piezoelectric device, not the device with these two parts. And I think that was the beginning of the project with Eckhart Quant.
Right.
Um, and I was wondering, are they not trying the other stuff? But then you started talking about the other projects that you have there in the big project. I'm
Should I
just
go back with the
wondering.
slides or not?
No, it is not
Yes.
necessary.
No?
I just wanted to ask. if besides these 4 parts that you presented today, that the groups are still working on different ideas besides these ones that you presented today, other kinds of materials, not just the concept of magnetostrictive or piezoelectric or the other part of the magnetic particles, or coils. If you are trying other kinds of concepts of materials, putting all this stuff together.
Yeah, I mean, most of them are based on the magnetostriction. So what was new, I would say, is for example, the surface acoustic waves. They have really a large bandwidth, and there are techniques to exchange bandwidth with sensitivity. So this is something that we can try. But it's all based on the basic idea, right? However, as you know, Rainer is always a pretty clever person with hundreds ideas per second or something like this. And they have also this piezotronic sensors, which I have not presented today. So there's a lot of new concepts also over there. However, the CRC is evolving. At the beginning, you are allowing a lot of ideas in the material science idea, but after a while, they should prove that they are good enough in order to move forward. Now it's more the focus. Of course, we have a lot of material science people, and we have also new professors that start contributing to the CRC. Now it's more on the system level. So instead of focusing on effects that could do something like piezotronic effects or whatsoever, they should have some time in order to show that they are good enough. Now it's the idea that we go on the system level. So do these individual sensors disturb each other? What are good amplifiers and so on? And this is currently the stuff. And later on, it will shift to medical dominance. And so, of course, we follow a few crazy or whatsoever concepts, mainly coming from Rainer, to be honest. But also like a converse electromagnetic effect is also new. This comes from the group of Eckhart. Maybe you know Patrick. You still know Patrick. He has worked on this, and these concepts are pretty promising because they have a very good, well, low noise and a low LOD, limit of detection. But he learns this actually in Russia. So he spends a couple of weeks in Russia, in St. Petersburg, I think. And there comes this idea of doing a readout magnetically with a pickup coil. So it's of course not the coil. There is, of course, a sensor inside that does something. So this principle is also new, but still based on magnetostriction. Anyhow, if you will have an idea of something completely new, then come over with this, be part of the CRC. But then you have to be good because, you know, we would like to reach the system level. Otherwise, we will change the applications to applications like DBS. Then we don't need that small signals anymore. We could live with stronger ones, but still we do something valid for medicine. The same is true for movement analysis. This is also new. So this could be done with the current sensors. So the application moved to the sensors and not vice versa now.
That is
I'm not
not,
sure if this answers your question.
that is the nice part of the project, that you're bringing this the concept that you started some years ago, and it is coming already to the device, and you are being able to use it. That is nice, and that you are having now. You have been talking to the industry just to produce this stuff. No, that's a nice part. That maybe
The problem was of this Corona. So this American, I mean, Boston Scientific has its headquarter. I don't know. I guess in Boston, but I'm not sure. But somewhere in the US, and they cooperate always via Zoom and stuff. But of course, they can send the newest electrodes, and also they put it in patients now. But it's not it's for all people not the easiest time for cooperation. But also, I like this that we have now. Even if it's basic research, they allow us to cooperate with industry in the perspective, and industry hasn't to pay anything. They just be good enough in their field, and then they can use this. And that's something where you can make sure that you really bring this stuff towards the people that need it, the patients, right? So this is something what I personally also really like. So
exactly that's nice. And just one more question, and it is related to the question that was asked before. Uh, I don't know if this Carlos Diaz was asking for a shielding box or something like that, just to avoid the magnetic fields coming from other parts. No, but then let's say that the sensor that you are using nowadays is not good enough. That the signal to noise ratio is very low. But that we know already more or less how is the behavior of the sensor, and more or less how is the behavior of the noise that you may have from all the instruments or the ambient or whatever. Don't you think it is possible to compete in that way? Maybe it is a very low signal and the signal to noise ratio is very bad, that you can come to with your all your expertise on signal processing to be able to at least determine how is the shape of the signal in certain way, or to detect certain aspects with this sensor that it is not good, we will say. I'm not saying that the sensor that you're using now is bad. No, I'm saying that it is, if it is not good, could you overcome all these problems of noise, even if you don't see the signal, and because the noise is very high, that you could come to an answer how, or to detect some stuff there, no, even if the signal is too noisy.
Well, first of all, you must make sure that the
Yeah.
sensor is actually working in. I mean, we have this shielded chamber. That's nice, and we can test there. But at the very end, it has to work in a normal environment in a hospital, and that's okay because we can check if a DC field of whatever 50 picotesla, 50 microtesla or whatsoever is not saturating the sensor or something like that. That's okay. So now the question is, how deep can we go with low amplitude signals? And then I cannot, be a sorcerer or something like that. But for example, in the group of France, they have these DeltaE sensors, and now they make them really small. So really, really small, and they use 100 or 200 sensors in parallel, and they have amplification circuits, so dedicated small circuit boards that actually do a readout. The hope is that the noise in all of these sensors is slightly different, but the desired signal is the same. And then you can average, and then you win something like the square root of n, if n is the number of sensors. So that's the first idea. The other idea is that you use tricks in the readout in order that you say, I excite something, and the excitation actually is compressing a lot of signals. I try to explain this, maybe not good enough. This could also help. So all the ideas from whatever amplification circuits that you know, from materials, Jeff is optimizing the domains that are creating. So try to find something where you avoid domain walls. So they should slightly change from, this is material optimization. And if everyone does its best, there is the chance that it will work at the end. This is something that we have proven during the writing of the proposals. However, you never know what was not thought about. And at the moment, it's open. To be honest, it's still open. Whether we would be able to measure, for example, a heartbeat with our sensors or not. For some applications where you can, for example, average quite long, DBS, you can put the people for half an hour or just for a second, measure them, then you can always win because the DBS electrode will always produce the same signal. So temporal averaging is possible, and it's just a matter of time how long you would average. On the other hand, you don't want to put people for half a day in the shielded chamber. Then I don't know what they do there, but anyhow. So, and it's open, to be honest. So maybe we win, maybe not. But it makes it also funny. Or that if you know who's the murderer at the end, then the crime story is not that nice.
Yeah, I'm sure you're having fun with this project, and congratulations that you are now the spokesperson.
I'm not sure. You have a lot of work, so maybe this is a good, maybe not. So let's see. But anyhow, I like it. Okay.
Okay, just Thank you very much. I don't know if anyone else have some more questions. I think no. I'm not sure. But yeah, if you could then let me know the webpage of the proposals in order
Mhm.
for the students to apply, probably,
I
then
will.
it will be perfect. And then I will share this link with the students. Thank you for the invitation also to participate in this. I mean, for the master students or the PhD students. That's very nice.
We
And
have often new jobs, PhD jobs. So if someone is really good or want to join, then let me know. I will send this. I want to go for a swim now, so I have to hurry.
cool. Okay.
So I will do it over the weekend, but on Monday you have this link, okay?
Okay, sure. Thank you very
It was
much.
a pleasure to see both of you, really. I mean,
Yes, it was really nice to see you again. So
come to
just let
here
us
once.
take a picture and that's it, okay?
You take a
Okay.
picture, okay?
Yes, so
I try to
let's.
smile.
1, 2, 3. Yes. Thank you. Thank you very much.
Okay, bye-bye. Also,
Bye
bye to all
bye.
the listeners. Thank you for listening. Bye-bye.
Greetings to
Ciao,
everyone
ciao.
there. Ciao.